Solving exponential equations. This video will take a look at some examples of solving for a mystery value within an exponent where we can solve this equation without the use of logarithms. Solving exponential equations where logarithms aren't needed work out nicely because we will end up working with the very same base on either side of the equation. There's essentially a three-step procedure. Isolate the bases, that just means get it all by itself on either side of the equation. Match the bases on both sides of the equation, and once you've accomplished that, you can then equate the exponents and solve for x. This first example is intentionally made to be quite simple so that we can look at that and solve that by inspection. 2 to the exponent x plus 6 is equal to 32. Well, we know that the exponent would have to be 5. 2 to the exponent 5 is my 32, and in order to have that exponent as a 5, x has to be a -1. How can we justify that and show that that -1 is in fact the correct answer? Well, isolate the bases has already been accomplished for us. There is nothing but this base 2 on this side of the equation, and so we move to step 2. We match the bases on both sides, and that simply just means express your 32 as a 2 to some exponent, which is that 5. Once I have matched my bases, I will then equate my exponents. What that means is I'm just going to take these exponents and just work with them, because whatever makes this true would be the number that would make this exponent equal to my 5. And so I've matched my bases and I equate my exponents. And of course we solve this linear equation and justify that the answer is in fact that -1. So let's take a look at a series of examples where we get just a couple of different variations each time. In this case, we will have something to do for our step 1, isolating my base. I have a base of 9 here with an exponent of 2x plus -5 multiplied by a 2. So let's divide that 2 away so that we can isolate this base 9, get it all by itself. And 54 divided by 2 is 27. Now, I have a base of 9, and I could make a 9 with some exponent that still means a 27, but it's actually easier to take a look at this and recognize that both of these are a base of 3, or can be written as a base of 3. My 9, with its exponent, could be written as a 3 squared, and then I have power of a power situation here. And with my power of a power, I would multiply my exponents. And of course my 27 written as the 3 cubed, I would have matched my bases on either side, and then I'm simply going to take those exponents off and work with my exponents. Now don't forget, this is a distributive property situation where I'm going to distribute that 2 in. I could divide it away at this point in time, but then I'd be working with 3/2 as a fraction, or perhaps 1.5 as a decimal, and I just find it easier to distribute that 2 in. And we will add that 10 to both sides and divide away my 4. And so what number makes the original equation true? It's 13/4. You need a 13/4 right here, multiplied by 2, subtract 9, take that as an exponent on 9, multiply by 2, and you'll get your 54, the one mystery value that makes it true. This one, a little bit of a different variation. We had to divide away a 2. Here we need to move away my addition of 7. And so we'll just use our equation solving skills. We'll leave our base 2 here. And I will subtract 7 from both sides, leaving me with 64. And we recognize that 64 is a base 2 as well. 2 to the exponent 6 is a 64. I have matched my bases, and so I'll just work with my exponents. I keep wanting to make that a 3. 2x plus 2 is equal to 6. 2x is equal to that 6 minus my 2. So we get 2x is equal to 4, and x, divide away my 2. So the mystery value that makes this true, I need a 2 here. 2 times 2 would be 4. 4 plus 2 is a 6. 2 to the exponent 6 plus my 7 does in fact equal my 71. In this fourth example, we don't have to isolate our bases. That step is done for us, but we do have to recognize the common base between a 1/25 and 1 divided by 25, or 1/125th, is a base 5. I need a 2x minus 3 exponent and an x minus 2 exponent to stay constant. And my 5 cubed is in fact my 125. And I have a 1 over 5 squared. We can do this in a couple of steps. Power of a power here. And so my 1 over 5 squared can be written with a negative exponent, which then, of course, it would be power of a power as well. And so we can multiply those exponents. I've matched my bases, and so let's just work with the exponents, equate the exponents. Use my distributive property. We have 6x minus 9, negative 2x plus 4. Bring our x's over, 6x plus 2x. Let's kick this negative 9 out, add it on both sides. We get 8x is equal to 13, and again we get an odd fraction, something that we wouldn't be able to pull up by inspection. What does it take to make these equal? Well, I need a 13/8 here and a 13/8 here to be able to do all of the math and make those values equal on either side of the equation. Now, the next two examples are examples of exponential equations where I need to solve, and I can't just use the 3 steps that I've been using so far. If you'll notice, when I had my mystery exponents, I just had my bases on either side of the equation. Well, I can't, with any mathematical operation, work this into an equation where I just have my base 2's. Here we just had our base 5's, we just had our base 3's. No matter what I do here, I've got a subtraction situation here, and I can't subtract powers of the same base. And if I bring this 2x over to this side, I would be adding it to 24, and I'm stuck that way. I cannot seem to just isolate bases on either side. And so I have my variable in 2 different spots. And so what we have to do is we have to think about getting that variable in one spot. And we have to think about the idea of common factoring. I like to remind myself why I would have an exponent that has an addition of terms here. If I had powers of the same base multiplying by themselves, this 2 with an x plus 2 would have come from this situation. If I had base 2's multiplying together and I had different exponents on them, our first power law reminds me that I would have to add those exponents. And so I like to write it out to remind myself that I have got this 2x in both of those terms. And so if you remember your common factoring, this perhaps might be similar to a situation like if I had an x times a y plus an x, then I would have an x in each term, and algebraically we would have divided it out of each term and pulled it out front, and I would have had a common factoring situation where if I distribute this back in, I would get back to where I started. Similarly here, I'm not just going to factor out an x, I'm going to factor out the entire term 2 to the exponent x. And common factoring is essentially dividing it out of each term. So I'm going to divide it out of this term, divide it out of this term, pull it out front so that I have 2 to the exponent x. And if I take it out of this term, I'm just left with 2 squared minus. And if I take it out of this term, I would just be left with 1. And now I have accomplished putting my mystery variable x in a single location rather than having it in 2. And now I can solve it. This is just a 4 minus 1. which of course is a 3. And now I can employ my 3 steps where I isolate my base, divide away that 3, and we get 8. I will match my bases, and of course I can say that x is my 3 there, equate my exponents. Similarly, we've got a situation here where I have 8 with an exponent on each of those bases. And what I want to do is get it into a structure where I've got both of my mystery exponents on the same side as we had when we started on this one, and factor that base with the exponent out. So I'm going to leave this 8 to the exponent x minus 1 here. I'm going to bring this 7 over to my other side of my equation by adding 7 to both sides. And I'll subtract this 8 with an x minus 2 so that I've accomplished getting both of my bases on one side of the equation. Now I'm going to put in that step where I remind myself why I would have put these two equations or these exponents together, and I'm going to choose to think of it as an x and a -1 in a multiplication situation. Truly, a subtracting of exponents would have come from this, where we would have divided my exponents and I would have subtracted the x minus the 1, but that could be thought of as an 8 to the exponent -1 if I brought it up in the numerator, and it's just easier to think of factoring if I have them as multiplication here. And so this one I'm going to choose to think of as 2 8 bases with my exponents. And then of course I'm going to recognize that I have this 8 to the exponent x in both of these sets of terms, and so I'll divide it out of this term, divide it out of this term, pull it out front in common factoring, get it to one location rather than 2, and I've got 8 to the exponent -1 minus 8 to the exponent -2 left over, and I just simply have to deal with those as fractions. That is a 1/8 minus a 1/8 squared. And so if I get a common denominator, this is a 64, so I'll multiply top and bottom by 8, so I can have my common denominator of 64. And we get 7/64. And so I will multiply up my 64 and divide my 7 down. Our 7's cancel out, and we have 8 to the exponent x is equal to 64, which is, of course, an 8 squared. And I can finish it up by saying x, the mystery value that makes this true is to have a 2 here and here. Do your operations on either side and you would have an equal number. And so what we've done is we've solved several exponential equations where we've had to manipulate our equation. If we've got our base in 2 spots where we have our exponential or our mystery value, we might have to factor it out and then isolate our base, match our bases, and equate our exponents. The next progression would be to work with examples where I cannot easily get the very same base on both sides of the equation. Something perhaps like this. 5 with some mystery exponent is equal to 7. There's no way I can get a base of 5 on both sides of that equation, and so this is what logarithms are good for.